Theoretical limiting accuracy of a weight measurement. A very sensitive spring balance consists of a quartz spring suspended from a fixed support. The spring constant is alpha, that is, the restoring force of the spring is minus alpha x if the spring is stretched by an amount x. The balance is at an absolute temperature T in a location where the acceleration due to gravity is g. So part A, if a very small object of mass m is suspended from the spring, what is the mean resultant elongation of the spring? So x bar, which is mean resultant elongation, can be found by drawing the free body diagram for the small object with mass m. You can see that at equilibrium we have the weight of this object mg, so we have the presence of gravitational acceleration, and there is the restoring force alpha x bar, so the net force should be equal to 0, therefore mg must be equal to alpha x bar, or x bar should be mg divided by alpha. So this should be the mean resultant elongation. So let's look at part B. What is the magnitude delta x square bar, which is x minus x bar square bar, of the thermal fluctuations of the object about its equilibrium position? About its equilibrium position. So now we have found the equilibrium position x bar, and we're going to have fluctuations of the spring about this equilibrium position. So let me look at this carefully. I have the equilibrium position of the spring x bar, and then I'm going to have fluctuations about this equilibrium position, and so the fluctuation amplitude delta x will be x minus x bar. So we're talking about fluctuations about this equilibrium position. And for that case, we can write the potential energy of the spring to be 1 over 2 alpha delta x square. And if you look at the average value of this should be equal to 1 over 2 kt using equipartition theorem. So these 2's will cancel, and we will find that for this one, delta x square delta x square bar will be equal to kt over alpha. Now, as you can see, this delta, we have to be careful here about what this delta x means. So we have a new equilibrium position x bar. We're looking at oscillations about this equilibrium position. So that delta x is what goes into the potential energy equation 1 over 2 alpha delta x square. So this is equal to half a kt using the equipartition theorem. It becomes impracticable to measure the mass of an object when the fluctuations are so large that the standard deviation or root mean square of the magnitude of fluctuations is comparable to or greater than x bar. What is the minimum mass which can be measured with this balance? So in part C of the problem, we're looking at the standard deviation of the fluctuations, which is square root kt over alpha, and this should, when this is greater than or comparable to x bar, which is mg over alpha, we have a problem. So the critical mass will be m critical g over alpha when this is equal to square root kt over alpha. So if I take the square of two sides, the critical mass squared g squared over alpha squared is kT over alpha, and I will find that my critical mass should be, because I have one cancellation of alphas here, square root alpha kT divided by g. So my mass, minimum mass I can measure is this one, because when I have this mass, I have the fluctuations equaling the fluctuation amplitude, the standard deviation fluctuations equaling x bar, and it becomes impracticable to measure the mass of the object when these fluctuations are so large. So the smallest mass that I can measure, the minimum mass that I can measure, is square root alpha kT over g. So let's take a look at it again. We have a very sensitive spring. It's placed in a gravitational field, and there is a small object with mass m suspended from the spring, and as a result we establish equilibrium. The spring elongates to an average distance x bar, where the restoring force is alpha x bar, that is balancing the weight of the object. So alpha x bar equals mg gives us the mean elongation to be mg over alpha. And then we're looking at fluctuations about this new equilibrium position, x bar. So those are delta x, x minus x bar, and 1 over 2 alpha delta x square mean value, that's the potential energy, is half a kT using equipartition theorem. So delta x square bar is kT over alpha. And it becomes impracticable to measure the mass of an object when the fluctuations are too large. If the fluctuation amplitude is square root kT over alpha, that is comparable to or greater than x bar, the mean elongation of the spring, we have a problem. So the critical mass would be when these two are equal, and that corresponds to square root alpha kT over g of the minimum mass that we can measure. So as you can see, as the temperature increases, the minimum mass that we can measure increases. So it's better to do these measurements at low temperature.